there's actually two reasons I want to give this talk. One of them is just to mention Alex, who is applying for postdocs right now. So thought I'd mention that. So maybe check out the application. And second reason I wanted to give this talk was, I guess people don't usually dedicate talks to people, but I did want to dedicate this talk to Bob Strickarts, who unfortunately recently passed away just a few months ago. Anyway, so let's get started. So we're going to have n, which is a positive integer. I'll just get rid of the notation, I guess. So this whole page is going to be notation. So let's see. So we're going to have a set omega in, just take it to be an n-dimensional Euclidean space. We're going to let sigma be its boundary. For now, just take omega to be like compact. Its boundary is going to be like C infinity, smooth, nice enough to do whatever you want. We're going to have x on the boundary. We're going to have a unit exterior normal vector n at the point x. Let's see what else. Got a lot of notation, so this is going to take a little while. I want to have a vector field. So this is my omega again. And I'm going to have a vector field at capital X. And let's see, I think I need to move on the other board. So for any S. So the vector field, the usual thing. It lets us move our set. So for any S, omega S, it's just a set that's moved by the vector field. Okay, so this dotted region is omega S. Okay, and we want to focus on a normal component of the vector field on the boundary of the region. So I'll denote the normal component as F. Let's see what else. So I think I'm going to need the mean curvature. So we're going to define that as the divergence of the normal. So in particular, the mean curvature of a sphere will be positive and constant. Let's see. So this A, that's going to be the sum of squares of entries of the second fundamental form. So A, it's like a matrix of all the partial derivatives of the normal vector. If you'd like, I already used my, so this is standard inner product notation. Angle brackets are standard inner product. A question? No? Okay. Let's see what else. I'm going to have a Laplacian and a gradient. This is notation for the Laplacian and gradient on sigma. So Laplacian, that's like sum of the iterated second order partial derivatives. When I have a gradient on Euclidean space itself, I'm going to add a bar over top. So this is the gradient on Euclidean space. Yeah, actually, I should mention, so Bob Strickarts really liked the Laplacian. He called it the triangle at the center of mathematics, because it appears so often. Then we're going to have a Gaussian density. So this denotes the usual Euclidean length of a vector squared. I'm one of those people who likes a 2 in my Gaussians instead of a 4. but I guess not everybody's like that. Last bit of notation here. So we got Ornstein-Uhlenbeck integral operator. And so this is for any, say, measurable function. Just take it to be bounded, because that's all I'm going to really care about. Something like a Gaussian heat semigroup. Not quite a semigroup the way that I wrote it. Oh, and this parameter rho down there, I'll squeeze it in here. I'm just going to take this parameter rho to be positive between 0 and 1. So any questions about all this notation that I got here? No? Okay. I think I got it all out of the way. So we can start with the first thing. Okay, so now that I'm done all the notation. So I'm going to talk about variational proofs of isoparametric inequalities. I'll start with the usual Euclidean isoparametric inequality. Probably most of us know various proofs of this, but maybe a little less known is that there's a variational proof of it. So it goes like this. First saw this in Barbosa de Carmo. I'm sure other people studied it too. But yeah, so it goes like this. So we're going to let lambda be some real number that's not 0. And we're going to assume two things. First thing is the mean curvature of the surface is constant. Okay, if you've done these sorts of calculations before, you know this means that, let's say omega or sigma is a critical point. Of the surface area functional, okay? That's what it means to, well, it's a consequence of being critical point is you have constant mean curvature. It's the first thing we assume. Second thing we assume is that if we so let's see. So we want to make a statement about minimizing. So we don't want to make a statement just about critical points. We want to make a statement about surfaces, say, that minimize surface area, right? So minimizing means the second derivative of surface area, which I guess I'm writing a little bit funny way, but I'm writing integrate on the surface dx, so that's surface area. So you're minimizing, so you need this to be bigger than or equal to 0 whenever you preserve the volume. So this is, so I can write this as for any f such that the integral on the boundary is 0. Right, remember what was the f? The f was, it's the normal component of how the surface is being stretched around, yeah? So if you haven't seen this before, so integral f is 0, that means, kind of like in the picture, like the amount that we're stretching the surface out is sort of the same amount that we're stretching it inwards. And so integral of f of 0 means they sort of cancel each other out. You're preserving the volume of the region to first order. Okay? So the second condition means that the surface is a local minimum of surface area. Okay? And so those are your assumptions. Conclusion is, as you might guess, that the sphere is the only local minimum of your surface area. One thing that's nice about this theorem is that, as we see, we're identifying local minima. So we're not just saying anything about global minima. We're saying this is the only local minimum of the sphere. Another nice thing about the proof, it actually allows the surface to self-intersect itself. But I didn't necessarily allow that in my formulation, but the proof works that way. So I'd just like to briefly say how the proof works, because I think if I just say a couple details, it's actually really short. It's a proof sketch. So first thing, you start by getting an explicit expression for this second derivative. And hopefully the notation is clear. I didn't define sigma s, so this is the boundary of omega s. Hopefully that's okay. Yeah. Okay, so you get an explicit expression. It's like this, negative FLF. Where L is going to be Laplacian plus second fundamental form squared length. Okay? So this is Laplacian. Once again, I'll emphasize this is Laplacian on the surface. Okay? Second thing is you can identify, well, not quite an eigenfunction, but almost. Like you really understand what the L is when G is this function. Okay, so if I use this function, I apply the Laplacian to it, I use this condition, I understand what L is applied to G. It's just the constant that came from this condition here. And so what is the G? So we can think of this if we go back to think about the normal component of a vector field. So the vector field here, it's just like the point x itself. So you can interpret this, the vector field that goes along with this as a dilation of your surface, or a dilation of this at omega. Okay, but if you don't like that dilation explanation, just note, okay, you plug this in, you got this formula, okay? And then so you can complete that proof by using just f equals g plus constant. Where the constant is shown, right, there's an annoying thing here, right? You would like to use this and just plug it into this condition, but maybe its integral is non-zero, in which case you can't plug in this g into here. But so okay, you just subtract a constant or add whatever. Add a constant such that the integral of f is 0. So the integral of f is 0. And in fact, that's enough. That's you just plug. So what do I mean by done? You just plug this f into here. That is, plug this f into this formula. You'll see that the sphere is the only one where this quantity is non-negative. And that's it. Like, it requires a calculation, but that's it. So in some sense, it's kind of magic because we want to prove this isoparametric inequality, and there's a single function that sort of works for any possible, say, local minimum of this inequality. Okay? Okay, so that's kind of cool. And it turns out like analogous things happen in the case that I guess I'm perhaps more interested in, which is to just replace everything here with Gaussian instead of Euclidean. So I think this was first realized by McGonigal and Ross in 2015. But I'll say maybe it was influenced by Kolding-Minikadze. work which we've heard about a little in this conference from 2012, okay? So I can structure this statement the same, just by, like I said, change everything here to Gaussian. It's going to work almost the same way. So let's see, how's it going to be different? So, well, first of all, okay, so being a critical point for the Gaussian surface area, you satisfy a little different equation. Okay, you got this extra term here that comes from the Gaussian. Okay. So this is, maybe I should say what I'm actually doing. This is the variational proof of Gaussian isoperimetric inequality. I'm kind of squeezing this in here. I just want to be clear about what I'm doing. Yeah? Okay, it's the same thing. So I have integral. Now I have a Gaussian density here. The condition of being a Gaussian volume preserving means the integral against the Gaussian density is going to be 0 for the f. Okay, then the conclusion is sigma must be a hyperplane. Okay, so we have to worry about things being non-compact and whatever, but you can deal with that. The point is, you get a similar statement here. The only local minimum of Gaussian surface area is the hyperplane. Okay? And so once again, probably people know this mostly. And just like before, we can sort of perform the steps analogously to the Euclidean case. So, okay, we start out, we get a explicit formula, the Gaussian second derivative of the Gaussian perimeter. So it's going to be, again, integral minus FLF. But the L is going to be different. Okay, so this time the L is going to be minus x dot gradient. I don't have a plus 1, 2. So you get some extra terms that come from the Gaussian, okay? But this is like, and once again, I'll emphasize this is Laplacian on the surface, gradient on the surface. And we might recognize this is an Ornstein-Uhlenbeck differential operator on the surface. We have this extra curvature term, right? But morally speaking, it's Ornstein-Uhlenbeck. Yeah. Okay. Okay. It turns out something special about the Gaussian case is you can get an explicit eigenfunction. So before, we had this is equal to a constant, but you actually get an explicit eigenfunction here with eigenvalue 1. So let's fix some vector v. Then g is going to be v and x. Okay. So you get an eigenfunction with eigenvalue 1. What is the function? It's just a linear function of the normal vector. So we think back to, what does that mean? That means that this vector field is just a constant. So it corresponds to just taking your surface and just translating it. That's what this perturbation is corresponding to. Just translate your surface. Translate your set. And then you're done. Did we see why we're done? Just take this equation, plug it into here. Second derivative of the perimeter. When we use this g, it's going to be minus Vn squared. But we know second derivative has to be bigger than or equal to 0. So we have negative, a square is bigger than or equal to 0. That means that this quantity must always be 0. But I skipped a detail, right? So the detail that I skipped is that, remember, this inequality only holds when the mean, when the integral of the function is 0. So in other words, this only applies when the integral of this function is 0. So for all v's where integral vn is 0. Okay, but what v's satisfy this? Well, I don't know, but this is it's a linear function of v being equal to 0. So there must be at least n-1 dimensional set of v's satisfying this. So you're pretty much done. That means that, you think about how that could happen. Well, I have all these v's in R3. I have all these v's in a two-dimensional space. The normal vector has to be perpendicular to them. Okay, so it means that your sigma is one-dimensional. Okay, so it doesn't solve it all the way as I wrote it, but it almost does. Yeah. Everything is analogous, yeah? So it's kind of nice. You can see like analogous statements here and there. Okay, and I guess I got 5 minutes left. Yeah, 5 minutes? Okay. 6? Oh, 6 is better, yeah. Okay. All right, so in my remaining 5 or 6 minutes, I just want to point out, so I already pointed out, yes, there is, so I have the Euclidean perimeter, we got the Gaussian perimeter, analogous proofs. It turns out you can make, so there's a more, okay, I'm going to say many things really rapidly. For multiple, it turns out there's a generalization of minimizing Gaussian perimeter for multiple sets, where this equation still holds. And so this was exploited by many of us, including, so Millman and Niemann is the big paper there, where they use this and some other insights to find sets of fixed Gaussian volume minimizing their total Gaussian surface area when you have multiple sets, so not just one. And they partition Euclidean space, okay? So that's a really nice paper. But for a lot of our applications, we care about something more general than Gaussian perimeter. What we care a little more about is something called the noise stability, which is sort of a Gaussian heat content. So analogous stuff. Everything I wrote over there has analogies for what we call the noise stability, or the Gaussian heat content. Okay, so theorem. So part of this, I guess, is the part of this is starting with Jackson, taking less year 2. So I'm going to, once again, take that sketch of what we did over there and replace Gaussian perimeter with Gaussian noise stability. And in the case of stating it, I'll get to the noise stability and define what it is. Okay, so we're going to have a lambda, same as before, but now it's between 0 and 1. We're going to have this parameter rho for the Ernst-Uhlenbeck operator. Okay, so first condition, what does being a critical point mean for the noise? Okay, maybe first I'll actually write the second thing because that tell you what the noise stability is. So I have integral. It's integral of omega t rho indicator omega. Okay, so this is noise stability. Just take a set, and then I integrate it against the heat evolution of the same set. Okay. Signs get reversed, so I no longer want to minimize surface area. I want to maximize noise stability. That sort of ends up being equivalent when rho goes to 1 to that problem. But anyway, so this, we want it to be less than or equal to 0 now because we're maximizing for all f's. Equal 0. Okay, and being a critical point in this case means your constant. So I take my set, I run this Gaussian heat flow on it. It's going to be constant on the boundary. That's what it just, you do a little calculation, you'll see that's what it means to be a critical point, okay? Okay, then, so if you're a critical point and you are a local maximum, then sigma must be a hyperplane. Okay, so like same statement over there, but now we have our noise stability in place of the Gaussian surface area. And sketch of the proof, analogous to what I wrote over there. So I take my second derivative of this noise stability. Okay, it's going to be a little different now because I have an integral sort of operator, and so when I take its second derivative, the second variation part is no longer going to be a differential operator. It's going to be an integral operator itself. Okay. Maybe I don't even have. Maybe I just won't even write it. But so I'll just write equals minus integral. I'll write f. I'm going to have this extra term though. Which I won't put into the S. Okay, so things are a little different now, but they're kind of the same. But actually, you can make an analogy. So what was the key fact over there? The key fact was these functions are eigenfunctions with eigenvalue 1. We have a similar thing here. So S of these G, well, I guess I wrote G over there. It's going to be 1 over rho G times this thing. Okay, so once again, G is any linear function of the normal vector. Okay. Now it's not exactly an eigenfunction, right? And this is part of, the result was 2015. This result is just like last year or two. This is part of, at least for me, I can't speak to other people, why I was having trouble drawing the analogy between that result and this result is that this G is not exactly an eigenfunction because you have this extra thing here. But it almost is. And sort of when you realize what the answer should be, everything actually becomes really easy. So maybe we can see like you just plug this. So actually this is my F, so I can really change this to F. So it has the exact, you plug this into here. And just like over there, you'll see that the hyperplane is the only thing satisfying this. Okay, well not, it has to be one-dimensional. The only thing satisfying this thing are less than or equal to 0 are one-dimensional things, just like over there. And so maybe just, I think I'm out of time, so I'll just say really briefly. So once again, for our applications, we really also care about not just the noise stability of a single set, we also care about noise stability of a bunch of sets that partition Euclidean space. And this identity, if you change it the right way, it still holds. And so you can make a similar statement that you can make over there, which is if you have a bunch of sets maximizing the noise stability, then they're low dimensional. And yeah, anyway, I think I'm out of time, so I'll stop there. So thanks.